Welcome to the lesson 2, Physics in Hydraulics Pre-Introduction. So, don't be intimidated when you hear physics, because this is going to be some basic calculus. It's pretty simple, I promise, and we're going to go through it together. It's pretty basic and simple. You're going to see. And so let's get to the lesson. So first of all, in our previous lesson, we talked about what is hydraulics, right? And we said that hydraulics is basically transmission of force through enclosed liquids, okay? So let's talk about those liquids for a second. Compressibility. So what compressibility is, it's a measure of a relative volume change of a fluid, in our case a liquid because we're in hydraulics, as a response to a pressure change. So for example, you have a bottle, okay? So here's a little bottle filled with water, and you have a piston in this part, in the opening, and you push that piston, so you create a pressure change, right? The pressure rises because of this. And the volume of the water won't change. It's just gonna exert pressure all over the bottle, right? If you have, for example, air, nothing's gonna happen, right? The pressure is gonna change and air is gonna compress to a smaller volume, right? So we say that liquids are usually incompressible even though they're not incompressible. So they're compressible, but it's just a small, tiny amount that we just neglect. So we're going to say that fluids, in this case liquids, are incompressible. Okay, so Pascal's law. So Blaise Pascal was a French mathematician and scientist who was born in 1623, and he was a smart guy. We have to thank him for his law, because if it wasn't for this, we wouldn't have hydraulics today. So the whole science of hydraulics is based around Pascal's law. And before we go to Pascal's law, we have to say a little bit about pressure, okay? So this isn't correct. This should be 1. I'm terribly sorry. So this should be 1 here. Before we start, the equation for the pressure is force divided by area, okay? So you have, I call this the holy triangle here. So pressure is equal by force divided by area, or if you want to calculate the force, you can go force is equal pressure multiplied by area. So pressure is equal force over area. So we talked about compressible fluids, right? Imagine this is an incompressible fluid here, and we deal a certain force, F1, to this cylinder, and what happens? So basically Pascal's law states that a pressure change at any point in a confined incompressible fluid, right here we have an incompressible fluid that's confined, is transmitted throughout the fluid such that the same change occurs everywhere. And what that basically means is that the pressure change that we make here by exerting a certain force, it's going to be applied to everywhere in this bottle, okay? And we have 2 points. We have this little cylinder and we have the bottom of the bottle. And let's look at this calculation. So we have pressure 1 equals the force 1 that we're exerting, we're giving the force 1, divided by the area of this cylinder, okay? And pressure 2, which is the pressure on the bottom of this bottle, which is equal to force that is pushing on the bottom of the bottle divided by the area of the bottle, which is much, much bigger than the area of the cylinder, as you can see. And Pascal's law says that the change at any point in a confined incompressible fluid is transmitted throughout the fluid such that the same change occurs everywhere, which means the pressure is going to be the same, right? And so we say P1, pressure, equals pressure 2, right? So the pressure that we made here is equal to pressure down here. And we put those equations right here. So F1 divided by area 1 is equal to F2 divided by area 2, which basically means, if you look it up here, that the force on the bottom of the bottle is going to be much bigger. Why? Because we have the pressure 1 times the area 2, which is much bigger than the area here. Okay? Now let's look at this example and let's do some math calculations so you kind of get an idea what's happening here. So here we have an area A1 and we have a force F1 that we dealt on this. Let's say this is some kind of cork in this bottle. So we moved it and we made a certain pressure P1, which by Pascal's law has to be equal to P2 because this is an enclosed fluid, right? So we want to know how much will the force be on this bottom of the bottle if the force in the input side is 100 newtons. And we know that the area of this cork is 10 centimeters squared and the area of the bottom of the bottle is 50 centimeters squared. So we know that P1, so the pressure that we made by pushing this, is equal to P2, the pressure that is going to act on the bottom of the bottle. So we have P1 is actually equal to F1 divided by area 1, so force 1 and area 1, and that's equal to F2 divided by area 2. So if we do this like this, so we have F2 times A1. If we multiply F2 times A1, we get F1 times A2. And we have to find how much is the force. So in order to find only F2, we have to divide this entire equation with A1. Okay, so divided by A1. So we have F2 is equal to F1 times A2 divided by A1. And now we're going to put the numbers in, okay? So F2 is equal, so F1 we said is 100 newtons, okay? So 100 newtons times the area of the bottom of the bottle, which is 50 centimeters squared. So 50 centimeters squared divided by the area of the cork, which is 10 centimeters squared, divided by 10 centimeters squared. And centimeters squared cancel each other out. And this comes to F2 is equal to 100 newtons times 5. Okay, 50 divided by 10 times 5. And what we get for F2 is 500 newtons. So we get a bigger force. Because force is equal to pressure times area, and the pressure stayed the same, but the area increased. So when the area increased, the force increased as well. So you see, we dealt 100 newtons on the input, and we got 500 newtons down here on the output. Okay, so we saw that the force here is gonna be much, much bigger. So this is basically the same principle. It's only like a better representation. So if we have a force and an area, and we have an area that's bigger, we're gonna get a bigger force. And this is kind of a mousetrap, okay? And why am I saying that? Okay, so we know the law of conservation of energy. It states that we can't create energy and we can't destroy energy, right? And this kind of blurs the picture. You're seeing here, you're applying a force of 100 newtons, and here you're getting 500 newtons. So basically free energy, right? We are saved. The world is going to be a great place where we have free energy. Wrong. So there's no such thing as free energy. Remember that. And there's actually a funny little story that I wanna tell you. When I was a kid, we got a call on our phone, and there was basically some kind of telemarketer scam. And the guy called me up and he said, "Oh, you want a free vacuum cleaner? It's worth $1,000." And I was so happy and hyped. I ran to my father and I said, "Dad, this guy called me. We won a free vacuum cleaner." And my dad asked me, "Son, do you know which cheese is free?" And I said, "No, I don't know which cheese is free." He said, "The cheese in a mouse trap." So, as you can see, this is a mouse trap. I'm not a great artist, so it's not a great drawing. So what we forgot is work. And what work basically is, it's force times distance, okay? And yeah, you can give 100 newtons here in the input, and you're gonna get 500 newtons in your output. But you are going to sacrifice distance, okay? So there's no free work, no free energy involved. Let me illustrate this to you. Now, first of all, what is work? In physics, work is the energy transferred to or from an object via the application of force along a displacement. In its simplest form, it is often represented as the product of force and displacement, so force times the distance. Unit for work is the joule, which is basically Newton times meter. So the equation for work is force times the distance, or force times the displacement. So if you take a box and you move it for 10 meters, and you need a force of, let's say, 500 newtons, if you want to calculate how much work you've done by moving it 10 meters, you just take the force and multiply it with the 10 meters. Okay, let's animate this. So we push this cork with a certain force, F1, and we get a certain force, F2 here, which is bigger than F1. So F2 is bigger than F1. So cork 1 travels a certain distance, and then cork 2 travels a certain distance as well, but a smaller distance. Now let's take a look at this. Okay, so let's mark this distance D1, the distance of the first cork, and let's mark the distance of the second cork as D2. So we know that the area of the cork 1 is equal to 10 centimeters squared, okay? And let's say we moved it for, let's say, 15 centimeters. So this is distance 1, okay? And we have to find the volume, the displacement we made by moving the cork. So the volume is equal to area times the distance, okay? So the area that we made is actually, 10 centimeters squared times 15 centimeters. And what we get is 150 centimeters cubed. This is the displacement we made by moving this first cork. Now, because now volume stays constant, we didn't add any fluid to this big reservoir. Now, the volume that we moved here had to be the same to the volume that was moved here. So volume 1 has to be the same to volume 2, okay? And volume 2 is actually equal to the distance, d2, times the area 2, okay? And we said area 2 is equal to 50 centimeters squared, okay? So in order to find how much we moved this big quark, we have to say, so distance is equal to the volume 2 divided by the area 2. Now volume 2 is equal to volume 1, which is 150 centimeters cubed, right? So 150 centimeters cubed divided by 50 centimeters squared. 50 centimeters squared. So centimeters cubed divided by centimeters squared, we get centimeters. Okay, so we're gonna do this. And 150 divided by 50 is 3. So we get the distance of 3 centimeters. So that's actually 5 times smaller than the 15 centimeters we moved the first quark. And now let's calculate the same thing, but using work, the calculation for work. So D1 is equal 15 centimeters, okay? And we applied a force of 100 newtons. And we said we got the force of 500 newtons on the output, okay? So we know that the D1 is 15 centimeters, F1 is equal to 100 newtons, and F2 is equal to 500 newtons. And as we said, no free energy. So the work that we did is the same. So V1 is equal to V2. So it's actually the same on the input and output. And this is only theoretical because we don't have any losses. This is considered to be a 100% efficient theoretical contraption, but this doesn't exist. This is just for explaining how this works. So we have force 1 times distance 1. So this is actually work. Okay, we said work is force times distance is equal to F2 times distance 2. And we have to find distance 2. So we say distance 2 is equal to force 1 times distance 1 divided by force 2. And what we get is 100 newtons here times D1 is 15 centimeters. 15 centimeters divided by 500 newtons. 500 newtons. So D2 is equal to, so we can cancel newtons. So what we get is 1 divided by 5 times 15 centimeters. So 15 centimeters divided by 5 is 3. And we get 3 centimeters using the equation for work. This is it for the physics basics in Hydraulics 101. Thank you for listening and for staying focused. And remember, there is no such thing as free energy. If you see a video of a perpetual motion machine on the internet or anywhere, just remember the law of conservation of energy. And if someone tries to scam you, remember, the only cheese that's free is the one in the mousetrap. Have a great day.